Okay, so this was our LB-273 diffusion lab. The intro and main ideas. So the goal of our experiment was to find and compare differences and similarities between the Python simulation and in-class diffusion experiment. A term to know for this lab was diffusion, and that is the process of following the random movement of molecules, creating a net flow from a region of high concentration to a region of low concentration. The research questions that we aimed to answer were how the bead's position, velocities, and accelerations affected when exposed to these different solutions, and also how different solutions would impact the rate of diffusion in a sample of polystyrene beads over a brief time lapse. Our prediction was that the rate of diffusion would be affected when beads are exposed to different solutions due to the differing viscosities. And the viscosity solutions that we studied were cornstarch, deionized water, and soap water. So our findings, obviously we ran 3 trials, one with cornstarch, one with deionized water, and one with soap water. In trial 1, we had little to no movement that was observed in the experiment when we used cornstarch as the observable solution. In trial 2, we had deionized water. The beads observed showed a standard movement when observed in the experiment, and this would be common to see because this would be our control since no additional solutions were added to the water. And then finally we had the soap water, which movement was significantly faster in this experiment compared to the 2 other solutions. These were the models that we used to predict motion of the beads. 2 concepts that we used to describe these predictions were Newton's second law, which is an object in motion stays in motion unless acted upon by an opposing force. And then we also utilized the law of conservation, and the law of conservation states that the total energy of an isolated system remains constant and is to be conserved over time. So essentially energy is neither created nor destroyed in this, it's just transferred since these are elastic collisions inside of the experiment. And then finally, our system model that we decided to go with was a very basic system schema with 3 pieces acting on one another. So we had the 2 micrometer bead, the glass slide, and the solution. And the bead and the solution had contact with one another. The glass slide and the bead had gravity impacting one another. And then the solution and the glass slide had contact and gravity acting upon one another during the lab.
As mentioned earlier, the question we are trying to answer is how the position, velocity, and acceleration of the beads is affected when exposed to different solutions, and how does it affect the diffusion rate of the beads. In order to answer these questions, we designed an experiment to help us determine how different solutions affect the rate of diffusion of polystyrene beads within 3 different solutions: water, soapy water, and cornstarch. These solutions all have a different viscosity, which allows us to test different diffusion rates. In order to record data that is useful to determine the rate of diffusion between the 3 different solutions, the group used a bright field microscope paired with the program AMScope to view and record the velocities of the beads within the 3 different solutions. After all 3 trials were performed, the group used the program Tracker to track a specific bead from start to finish during a set amount of time for each trial in order to find the velocities of each different solution. The velocities of these beads is important because they can help you to determine how fast the beads diffuse. They can do this because diffusion is defined as the random movement of molecules from a region of high concentration to low concentration. The movement of the beads stimulates the movement of molecules, and the solutions that the beads are placed in supply the concentrations. The beads begin in the pipette in a very confined space, and when placed on the slide, the container size changes, which allows them to diffuse and evenly spread out. The rate at which the beads move once placed on the slide simulates the rate of diffusion because they prefer to evenly spread out, and once they are evenly spread out, they are at equilibrium.
As mentioned earlier, we have our processed results. We have position, velocity, and acceleration versus time, all on the same axes, 0 to 40, 0 to 40, and 0 to negative 35 for all 3 to easily compare the different solutions. So we have it in soap water, regular DI water, and cornstarch. As we can see in the soap water, there's a huge increase in position change, which is a velocity of 35 to 40, and an acceleration of negative 30 to negative 35, while in the position versus time in water, we see less of an increase in position change, velocity 15 to 20, and more of a negative 5 to negative 10 acceleration. Over here in the cornstarch, we really see minimal movement, and that continues on all 3 graphs. Some discrepancies, as we can see, it starts at 0 over here and 1 over here. That just depends on when we hit play. To do this, we used tracker software on a video obtained by a microscope, and so those are essentially the same. We also see a lot of fluctuations, and that could be because of human error, or it could be because of the software. So some scientific reasoning has to do with the viscosity of the solution, how thick it is, how sticky it is. So a less viscous solution has molecules with smaller masses, a more viscous solution has molecules with larger masses. Cornstarch is obviously more viscous than water, and soap water is going to be the least viscous of these 3 solutions. Therefore, cornstarch has larger mass molecules, a larger momentum vector equals mass times velocity vector of a molecule. Therefore, the momentum moving against the 2 micrometer beads in cornstarch is going to be much greater, much larger than that in the water and that in the soap water. So the ability for the 2 micrometer beads to move is related to the viscosity of the solution it's in. A less viscous solution will have less momentum against the 2 micrometer beads when colliding, allowing the beads to overpower the solution and easily diffuse, allowing the beads to continue on their normal diffusion path and not be stopped by the solution like seen in cornstarch. So that's all we have for you.